All right. To pick up where we left off on Lewis structures, with a couple simple examples to begin with, and then getting a little harder as we go on. Um, Strictly speaking, Lewis structures really only applies to covalently bonded molecules. What we draw for ionic compounds are really just a collection of Lewis symbols, technically. But anyway, uh, normally your goal when forming covalent bonds, again, when you're forming covalent bonds, you're only dealing with nonmetals. And when nonmetals bond together, their goal is generally to share electrons so that both of the nonmetals involved in the bond can have an octet of valence electrons around them simultaneously. And they do that by sharing electrons. And we can look at the example of fluorine, which is very similar to the example of chlorine that we saw a few minutes ago. So I won't spend a lot of time on this, but anyway, each fluorine has 7 valence electrons of its own. And the way I've drawn those electrons out here kind of makes it obvious how they fit together, because each one of the fluorines has an odd electron that will fill the gap in the other fluorine. And so they come together, they share those odd electrons as an electron pair. And now if you include all of the lone pair electrons on each fluorine, along with the pair of electrons that are being shared, you'll find that both fluorines effectively have an octet simultaneously. And so that's a good thing. It makes them much more stable than they would be on their own. When a molecule or when two atoms share one pair of electrons, like the fluorine atoms are doing in this case, that is considered a single covalent bond. A single covalent bond usually consists of one electron from each atom, like it does here, but there are some cases where both electrons might come from one of the atoms and none of them from the other atom. And again, the electrons that are shared between the atoms are bonding pair electrons, and those that are not shared between the atoms would be lone pair electrons. So the F2 molecule has one bonding pair of electrons, and it has 1, 2, 3, 4, 5, 6 lone pairs of electrons. Okay, you can also represent each pair of bonding electrons with a dash. And the reason you might want to do that is if you want to emphasize the bond rather than how many electrons are involved. So the F2 molecule, like we drew it up here, could also be just as correctly drawn as F dash F, and then each fluorine having 3 lone pairs of electrons around it. And so the dash represents one covalent bond, but of course that one covalent bond consists of 2 shared electrons, and so you can write it either way. It's just a different emphasis depending on how you write it. After doing a few Lewis structures or a few dozen Lewis structures, sometimes you get really sick of drawing little dots anyway. So you just want to do a dash for something, just for something different. The atoms in covalent bonds can sometimes share more than one pair of electrons. And that's in cases where sharing one pair of electrons doesn't get them to an octet. And there are lots of cases like that. And in that case, they will usually just share more than one pair of electrons. A good example of that is oxygen. Each oxygen atom has 6 electrons. And drawing it like this, pairing up the pairs of electrons, drawing the electrons individually as much as possible, and only then pairing them up, gives you 2 pairs of electrons and 2 lone electrons on each oxygen atom. And that kind of clues you in right away that this is 2 places where there can be bonds formed. And sure enough, that's what happens. If you try forming a single bond between the 2 oxygen atoms, that is, say, the oxygen atom on the left shares this electron, and the oxygen atom on the right shares this electron, you get this structure here. And each oxygen atom, it has 1, 2, 3, 4, 5, 6, 7 electrons around it. Same on the right and the left, 7 electrons again on the right. And that's not an octet. So what they do is they basically do the same thing again. you can move the electrons on the Lewis structure around in order to get them to the position between the two atoms so that they can take part in a bond. That's something that you're able to do. And so in this case, whoops, I didn't draw that circle quite right. Let me get rid of the circle and I'll draw it again. So what you end up with is essentially this. These two electrons here on the bottom will now be moved to a position between the two atoms so that they can be shared by both atoms simultaneously, and you have something that looks like this. If you look at the electrons around the oxygen on the left, you'll find that you have 1, 2, 3, 4, 5, 6, 7, 8. And if you look at the electrons around the oxygen on the right, you'll find that you have 1, 2, 3, 4, 5, 6, 7, 8. So now, with the oxygen atoms sharing 2 pairs of electrons, you have an octet around each oxygen atom, and that makes it much more stable, and that's the way oxygen actually is found. You could also write this as O double line O, and then each of the oxygen atoms has 2 lone pairs of electrons on it. That means the same thing as what we drew here. It's just a matter of whether you want to emphasize how many bonds there are, which in this case emphasizes that it's a double bond, or how many electrons are involved, which in this case emphasizes that a double bond consists of 4 electrons being shared. 2 pairs, in other words. So sharing 2 pairs of electrons between 2 atoms would be a double covalent bond. Sometimes even that's not enough, though. Like if you look at the example of nitrogen, this gets a little crowded, so I did it over again on the next page. Each nitrogen atom has 5 electrons or 5 valence electrons, that is, because it's in group 5A. And so we have 1, 2, 3, 4, 5. If you draw the electrons singly around the 4 sides of the symbol and only then start pairing them up, you would go 1, 2, 3, 4, 5. So you end up with 1 pair of electrons and 3 electrons that are not paired. And that right there kind of clues you in that maybe you're going to need 3 bonds to get nitrogen to an octet. And that's exactly what ends up happening. You can make the 2 nitrogen atoms share 1 pair of electrons, in which case each nitrogen atom has 1, 2, 3, 4, 5, 6 electrons around it. That's not good enough. So it's not a single bond. Try it again. Bring 2 more electrons together between the nitrogens and form a double bond. And now each nitrogen would have 1, 2, 3, 4 shared electrons plus 5, 6, 7 lone electrons. That's 7 electrons each. Closer, but not good enough. So it's not a double bond either. You still got 1 more lone electron in each nitrogen. So let's bring those between the 2 nitrogen atoms. And so the nitrogens will be sharing 3 pairs of electrons. And now each nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And that is an octet. And so that is what you actually get, a triple bond. And you could also write that as N triple line N, with each nitrogen having 1 lone pair of electrons on it. And that really means the same thing as the Lewis structure we drew. It's just that the one with the lines emphasizes that it's a triple bond, and the one with the dots emphasizes that there are 6 electrons or 3 pairs being shared. Okay, so like I showed in the last couple of examples, you can often predict how many bonds will be formed by a nonmetal from the number of electrons needed to reach an octet. Because like I said, generally, when you form covalent bonds, each atom involved in the bond will gain 1 electron for each covalent bond. So if an atom forms 1 covalent bond with another atom, then each of those 2 atoms effectively gains 1 electron. If 2 atoms form a double bond, then each of those atoms effectively gains 2 electrons, and so on. And so just looking at the elements, as we've seen in the last couple of examples, chlorine has 7 valence electrons, and it needs 1 more electron to reach an octet. So chlorine almost always forms single bonds. Oxygen has 6 valence electrons, and it needs 2 more to reach an octet. So oxygen almost always forms two bonds. Now, those two bonds could take the form of a double bond, like oxygen forms with other oxygen atoms, or it could take the form of two single bonds, like it forms in H2O. Nitrogen has 5 valence electrons and it needs 3 more to reach an octet. That means nitrogen almost always forms 3 bonds in its compounds. And those 3 bonds could be 3 single bonds, or it could be one double bond and one single bond, or it could be one triple bond like it forms with other nitrogen atoms. But either way, the number of bonds around the nitrogen will almost always add up to 3. Carbon has 4 valence electrons, and that means it needs 4 more to reach an octet, and that means that carbon almost always forms 4 bonds. And there is an entire branch of chemistry known as organic chemistry that is based on this fact. And it always keeps coming back to the fact that carbon always forms 4 bonds. Those 4 bonds could take the form of 4 single bonds, or say 1 double and 2 singles, or 1 single and 2 doubles, or 1 triple, 1 triple and 1 single, or 2 double. Anyway, the total number of bonds has to add up to 4 for carbon, and other things in those same groups. So this applies, what I said about chlorine applies not only to chlorine, but also fluorine and bromine and iodine. And what I said about oxygen applies not only to oxygen, but also to sulfur and selenium and tellurium. And what I said about nitrogen also applies to phosphorus and arsenic. And what I said about carbon also applies to silicon. And below the zigzag line, remember, now you start getting into the metalloids and metals. So sometimes they behave a little differently. But anyway, as long as you're above the zigzag, then what I said about the number of bonds they form, that stays the same for anything in that group. Now, there are exceptions to the octet rules. Before we start getting into actually drawing Lewis structures for molecules, it's good to know that there are some exceptions to the octet rules. One of them I mentioned already, and that is that transition elements generally don't follow the octet rule. And that actually generally comes down to the way we define the valence shell for transition elements. And that's basically why they don't follow the octet rule. There are also some elements that are called electron deficient. In that they can be satisfied with less than an octet of valence electrons around them. And that's because they're very small atoms. And if you try to fit 8 valence electrons around them, you get into issues of crowding. There just isn't enough room because of the repulsion of electrons for each other, because they all have negative charges, and negative charges repel other negative charges. You just can't fit an octet of electrons around some of these atoms. And so some examples would be hydrogen and helium, which are satisfied with 2 valence electrons around them. Hydrogen is especially important because you encounter that a lot in Lewis structures. And so, it's good to keep in mind that you do not want an octet of electrons around hydrogen. And also the fact that hydrogen only gathers 2 valence electrons around itself means hydrogen can only form 1 bond, because sharing of 2 electrons is 1 single bond. And so another thing to keep in mind is that hydrogen will never be the central atom in a molecule. Hydrogen can only occur around the outside of a molecule, because it can't be in the center if it can only have something on one side of it. Beryllium can be satisfied with 4, beryllium here can be satisfied with 4 electrons around it. Boron and aluminum can be satisfied with 3 pairs of electrons or 6 valence electrons around them. Although that doesn't mean that they will never have an octet, but they can be satisfied with 6. So if you end up with a structure for a simple molecule and it has boron or aluminum in it, don't be surprised if you only have 6 electrons around the boron or the aluminum. That doesn't mean that you're wrong. On the other hand, some atoms can accept more than an octet of electrons around them, and that is specifically the larger nonmetals in the third period of the periodic table and below. These are known as hypervalent elements, and they would include things like, say, phosphorus, silicon, sometimes chlorine, arsenic, selenium, bromine, iodine, tellurium, things like that. So basically these guys here can often have more than an octet of electrons around them. And some examples of that would be sulfur in sulfur hexafluoride, definitely has way more than 8 electrons around it. Xenon in xenon tetrafluoride or xenon hexafluoride has more than an octet of electrons. Phosphorus in phosphorus pentachloride has more than an octet also. And another category of exception would be molecules or ions with an odd number of electrons, which are also known as free radicals. It's especially common with nitrogen compounds. So for example, nitrogen monoxide or nitrogen dioxide, both of those compounds have odd numbers of electrons. And so there's going to be one atom in the compound at least that doesn't have an octet of electrons around it, because in order to get octets around everything, you would need an even number of electrons. Okay. Okay, so a lot of times, some of the simpler Lewis structures, like in Cl2 or HCl or CH4, can just be put together by inspection. So if you want to connect one carbon with 4 chlorine, or with 4 hydrogens, I mean, you just draw the Lewis structure for carbon, which if you draw it probably the preferable way, would be carbon surrounded by 4 separate dots, one on each side. And then you would have 4 hydrogens, each with 1 dot around it. Becomes pretty clear how they fit together. Each hydrogen shares its electron with one of the electrons from carbon, and you end up with this structure here. Carbon with basically all carbon hydrogen single bonds. Carbon, you'll notice, has an octet of electrons around it, 2, 4, 6, 8. But hydrogen, each hydrogen only has 2 electrons around it, because hydrogen is satisfied with 2 electrons. It doesn't want an octet. This structure could also be drawn like this, with lines instead of the 2 electrons. Remember, each line is 2 electrons. Okay. More complicated molecules, though, often require a sequence of rules. And because some of them can get pretty complicated, and putting them together by trial and error could take you a very long time. You may never get it right. So if you follow these rules in this order, and this is the same order, the wording I used may be a little different than what the book uses, but the order is the same, and telling you to do the same things as what's in the book. If you follow these rules in this order, you should be fine for anything that we would encounter in this class. In general chemistry, we're generally dealing with molecules where there's one central atom, that is one atom in the middle, and it will be surrounded by other atoms that are bonded to the center atom, but not to each other. So something like, generally, you've got one atom in the center, and then you've got other atoms around it in various places, and those atoms are bonded to the center atom, but they're not bonded to each other or anything weird like that. So for molecules like this, if you follow these rules in this order, you should be just fine. And the rules in order would be, first of all, you want to determine, and I'll show a couple of examples after I go over the rules. Determine the total number of valence electrons in the structure. To do that, you add up all of the valence electrons in all of the atoms in the molecule according to the periodic table. And if it's an ion, then you add 1 electron for each negative charge. So if the charge is like -2, you would add 2 electrons. Or you subtract 1 electron for each positive charge. So if the charge is +2, you would subtract 2 electrons. Then you arrange the atoms in what's known as the skeletal structure. And as I said, most molecules that we encounter in this class will have the central atom surrounded by other atoms bonded to the central atom, but not bonded to each other. The central atom will most likely be either the least electronegative element in the molecule or the unique element in the molecule. That is the element that you've only got one of in the molecule. And very often, those two will be the same. You know, the least electronegative element will be the one that you've only got one of. If they're different, then more often than not, it'll be the unique atom that goes in the center rather than the less electronegative one. So at least electronegative, I'm going to underline that because that generally takes precedence. Or sorry, not least electronegative. Sorry, I meant to do it the other way. It's the unique atom that usually takes precedence. Not always, but usually. Then connect each outer atom to the central atom with a single bond, that is a pair of electrons for now. Okay, that's one pair of electrons. Now we may change that to a double or even a triple bond later, but for now, we'll make it a single bond. Now remember, we've got a certain total number of electrons here that we're not allowed to exceed, but we do have to make sure that we use all of them. So we have to come in right on target. So there should be electrons remaining at this point, or there usually will be electrons remaining at this point. Use them to fill in octets around the outer atoms. Just remember, hydrogen does not want an octet. And also hydrogen will never be in the center. Remember that too. If any electrons remain after completing the octets around the outer atoms, then place those remaining electrons on the central atom in pairs. So there will be lone pairs on the central atom if there are any electrons remaining at that point. Then you basically look at the central atom, and if it still doesn't have an octet of electrons around it, then you might have to make double or even triple bonds with one or more of the outer atoms. Okay, so that is something to keep in mind as we do some examples here. First of all, the nitrate ion. The nitrate ion has the formula NO3 minus. We can draw a Lewis structure for this because the nitrate ion is basically just an atom, or sorry, basically just a molecule with an electrical charge on it. And we can account for that electrical charge just by adding one more electron. Okay, so NO3 minus, nitrogen has 5 valence electrons. We also have 3 oxygens at 6 valence electrons each. That's 18 valence electrons. And then we have the negative charge, which is equivalent to adding 1 electron. And then when we add all of these up, 18 plus 5 plus 1 is 24 valence electrons in this polyatomic ion. We set up our skeletal structure. Here we've only got 1 nitrogen, so that means that that's probably in the center. Nitrogen is also less electronegative than oxygen, which is a good sign. So nitrogen's definitely in the middle, and the oxygens will be around the outside of it. It doesn't really matter for a Lewis structure. It doesn't matter where you draw the oxygens because the Lewis structure isn't really about showing you what the molecule really looks like. The Lewis structure is about showing you how the atoms are bonded to each other. And then we can take that information later and use it to figure out what the molecule really looks like. Okay, so it doesn't really matter where you draw the oxygens as long as they're around the nitrogen somewhere. Okay, we've got 24 electrons. We know that's our total. The next thing you would want to do is attach the oxygens to the nitrogen with single bonds, keeping in mind that each of those bonds is 2 electrons. So we've used 2, 4, 6 electrons so far. Then we use the remaining electrons to complete octets around the outer atoms, being careful not to go beyond the total. So far we've got 2, 4, 6 electrons, and now we can go 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Just made it. Okay, so we've got 24 electrons total. The oxygens all have octets of electrons around them, but what about the nitrogen? The nitrogen has 2, 4, 6 electrons around it. The nitrogen does not have an octet of electrons around it. That's a problem. And so this is basically step 5. If the central atom still doesn't have an octet of electrons around it, try a double bond with one of the outer atoms. In this case, the outer atoms are all of the same element, and so it doesn't matter which of them we choose to participate in a double bond. Well, all that really means is we're going to take one of the lone pair of electrons from one of the outer oxygens and move it to a position between the nitrogen and the oxygen. Okay. And just remember, when you go drawing, when you draw the new structure with the double bond and you go to draw the lone pairs of electrons, just remember that pair of electrons has moved, so it's not on the oxygen anymore. So this double bonded oxygen only has 2 lone pairs of electrons on it now. And now the nitrogen has an octet of electrons, 2, 4, 6, 8. And so that is our structure for the nitrate ion. And you should draw brackets around it and put a negative sign outside the brackets because it is an ion. It does have a negative charge. So that is the Lewis structure for the nitrate ion. If you chose this oxygen or this oxygen to have the double bond, that's fine, as long as the double bonded oxygen only has 2 lone pairs of electrons on it, while the single bonded oxygens have 3 lone pairs. Okay. Another example we could do would be the molecule SO3, sulfur trioxide. And you might think, oh, that's going to be really similar to NO3, but actually it's not, because sulfur is in a different group from, actually it does come out a little too similar. I wanted to try SO2. That's what I wanted to try. That comes out a little different. SO2, sulfur dioxide. Okay, in this molecule, we've got sulfur, which has 6 valence electrons. And we've got 2 oxygens, which is 2 times 6. And that's a total of 18 valence electrons that we have to account for. In this case, we've got a single sulfur, and also sulfur is less electronegative than oxygen because electronegativity goes up as you go up a group, so oxygen is more electronegative. So oxygen is second only to fluorine, so oxygen is going to have more electronegativity than anything else in the entire periodic table except fluorine. And so sulfur definitely goes in the middle, and we put an oxygen on either side of it and connect it to the central atom with single bonds so far. This is 1, 2, 3, 4 electrons we've used so far. We've got a total of 18 we have to account for. So we've used 1, 2, 3, 4, and now we put lone pairs on the outer oxygens. So we've used 4, so this is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've only used 16 electrons so far out of a total of 18. So if you, again, if you have any electrons left over after creating octets on the outer atoms, you put them on the central atom in pairs. And that just means that you draw 2 dots over the S. And so now we've used all of the electrons. The next thing to do would be check for octets. We made sure that the oxygens both have octets, but what about the sulfur? 2 electrons in each bond, so that's 2, 4, 6. That's not an octet. What that means is you're going to need a double bond. And in this case, both oxygens are equivalent to each other, so it doesn't matter which oxygen you choose. Just have one of the oxygens move one of its lone pairs to a position between itself and the sulfur, and that will form a double bond. And remember that lone pair is not there anymore, so don't draw it in the new Lewis structure. And so there is your Lewis structure for SO2. Okay, and then one other I wanted to show. I'm trying to get in as many oddities and sort of not necessarily rule violations, but as many odd things as possible, so you can kind of see an example of just about everything. Xenon tetrafluoride, one of the very few compounds formed by noble gases. Xenon has 8 valence electrons around it, being one of the noble gases in group 8A. We've got 4 fluorines, so that's 4 times 7 electrons each. And when we total that up, we get 4 times 7 is 28, and 8 is 36. 36 electrons is our total. So we put the xenon in the center. Fluorine is the most electronegative element of all, so xenon is definitely less electronegative than fluorine. And there's only one xenon, so there's no doubt xenon is in the center here. And then we would want to put the fluorines around the outside. Again, you can position them really any way you want for a Lewis structure. It doesn't really matter as long as they're around the outside of the xenon somewhere. And we would connect the fluorines with the xenon with single bonds to begin with. 2 electrons each. That means we've used 8 electrons so far. And now we want to complete the octets on the fluorines. So we've got 8 electrons, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. 32 electrons. But we have a total of 36. That means there are 4 electrons left over. We need to put them on the central atom in pairs, so that would mean 2 pairs. And I'm just going to draw them on opposite sides here because, electrons repel each other, so I figure they'll probably get as far apart as possible. And so I'll just draw those 2 pairs of dots right on the xenon. And this will be your Lewis structure. We know that the fluorines have octets because we made sure of that during the procedure. And the xenon has, let's look at the xenon. 2, 4, 6, 8, 10, 12. The xenon actually has 12 electrons on it, but that's actually okay because xenon is one of the nonmetals that's below period 3. It's a very large atom, so it can accommodate more than an octet of electrons if it has to. And in this case, it does have to, because that molecule definitely does exist. And the only way it can exist is if xenon has more than an octet around it. So it's got to have more than an octet. So there you go. There's an example of a hypervalent compound. If we had one other I can think of, electron deficient, AlCl3. Aluminum chloride. Aluminum only has 3 valence electrons. Each chlorine has 7 electrons, and there are 3 of them, so that's 21 plus 3. That's 24 valence electrons on this molecule. Aluminum is a metal, so that will definitely be less electronegative than any of the nonmetals. And chlorine is one of the more electronegative metals, so aluminum definitely goes in the center. And we put the chlorines around the outside and connect them to the aluminum with single bonds, at least for now. And let's see, that's 2, 4, 6 electrons. Then we want to complete the octets around the chlorines. So we got 6 electrons so far, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There you go. And so we've got octets around the chlorines, 2, 4, 6, 8 for each of them. But around the aluminum, we've only got 2, 4, 6 electrons. And you might think that that's a problem, but remember, aluminum is one of the atoms that can be satisfied with less than an octet. So 6 electrons is okay for aluminum. The only way you could get an octet of electrons on the aluminum would be to force one of the chlorines to form a double bond with aluminum. And as we saw before, chlorine has 7 valence electrons of its own. So chlorine generally only wants to form 1 bond each. And trying to get chlorine to form a double bond would be very, very difficult and highly unlikely. So this is the Lewis structure for aluminum chloride. Okay, well, we're over time on this lecture, so I'll try and make the next segment a little shorter. But anyway, that's drawing Lewis structures, and we'll move on to other stuff in segment C.